Hi everybody, welcome to our module on pulmonary physiology. So there's a bunch of smaller topics that all fall under the subject heading of pulmonary physiology, and we'll go through them all in this module. You need to know, especially for step one, about lung volumes and capacities, about ventilation and dead space, about lung and chest wall pressures, and then finally we'll talk about the compliance of the lungs and a little bit about airflow resistance. So let's start by talking about lung volumes. And the first thing to know about lung volumes is the average person can only inhale about 6 liters of air. That's the most you can fill your lungs on average. You also should know that no matter how hard you try to push the air out of your lungs, you will never be able to get the volume down below about a liter or so. That air that's always left inside your lungs, no matter how hard you push out, is called the residual volume. Now, when you're not thinking about breathing and you're not trying to inhale deeply or exhale vigorously, that's called quiet breathing. And when you're breathing quietly, your lungs are inhaling air such that they go from about 2.5 liters up to about 3 liters and then back to about 2.5 liters. And this amount of air that's going in and out with each quiet breath is called the tidal volume. That's the amount of air that goes in and out with quiet breathing. Now, if you try to inhale as deeply as you can, you will fill your lungs all the way up to their maximum capacity, that 6 liters amount. That's called the total lung capacity. And that extra volume of air that you drew in above your tidal volume is called the inspiratory reserve volume. That's the amount you can inspire if you try really hard, the extra air beyond the tidal volume. Additionally, if you exhale as hard as you can and push out as much air as possible, you will put out an extra volume of air beyond the tidal volume, and that extra volume of air is called the expiratory reserve volume. And then a final number that I want to mention here is the amount of air that's inside the lungs at the end of a quiet breath, which is shown right here in this picture. That's called the functional residual capacity, and that's a very important volume because that's where the lungs come to rest at the end of a quiet breath. And we'll talk later about how the fact that the FRC is where the forces inside the lungs are balanced, and that's why you end up there at the end of a quiet breath. So I mentioned a lot of things in that picture, so let's review them because they're important. There are 4 volumes that you need to know. The first is the tidal volume. This is the air that goes in and out with each quiet breath. The next is the expiratory reserve volume. This is extra air that can be pushed out with force beyond the tidal volume. And after you push out that expiratory reserve volume, all that remains in the lungs is the residual volume. Then there's the inspiratory reserve volume. This is extra air that can be drawn in with force beyond the tidal volume. And when you inhale the inspiratory reserve volume, the lungs will be filled to capacity. And then finally, there's that residual volume, that air that can't be blown out no matter how hard you try. In addition to the 4 volumes, there are 4 capacities that you need to know, and a capacity is a sum of at least 2 volumes. So the first one is the total lung capacity. This is a sum of all the volumes in the lung, the residual volume, the expiratory reserve volume, the inspiratory reserve, and the tidal volume. The next one is the inspiratory capacity. This is the most air you can inspire. So it's the tidal volume, which is what you inspire with a quiet breath, plus the inspiratory reserve volume, which is that extra volume you can inspire with force. And then the third capacity is the vital capacity. This is the most you can exhale. So this is the tidal volume plus the inspiratory reserve volume plus the expiratory reserve volume. This is everything but the residual volume, which is that little bit of air that you just can't get out of the lungs no matter how hard you try. And then the fourth capacity you need to know is that important functional residual capacity. This is the residual volume after a quiet expiration. It's equal to the residual volume plus the expiratory reserve volume. It's the volume when the system is relaxed, and that means that the chest wall force pulling out equals the lung force pulling in. And this is going to be important later when we talk about these 2 forces and how they balance to determine the FRC. So I'll give you a trick I use to remember the volumes. I just remember them in this order: RV first, then ERV, then IRV, then TV. And if you remember them in this order, then the bottom 2 are the inspiratory capacity, the bottom 3 are the vital capacity, the top 2 are the FRC, and then finally all 4 of them together are the total lung capacity. I don't know if that helps you, but that's how I've always kept them straight. So the next pulmonary physiology topic we're going to discuss is ventilation. So ventilation equals the volume of air you breathe times the frequency of breathing, which is the respiratory rate. So for example, if you took in 500 cc's of air per breath times 20 breaths per minute, that would be a ventilation rate of 10,000 cc's per minute, or 10 liters per minute. Now there are 2 places that all that ventilated air goes. The first place is to the alveoli, and alveolar ventilation is very useful for gas exchange because the alveoli are where red blood cells can pick up oxygen. However, some of that air goes to what's called dead space, and this is ventilation to areas where gas exchange can't occur. It's wasted ventilation. So air that goes to the nose and the trachea and other areas with no gas exchange is called dead space ventilation. So let's talk about dead space in a little more detail. As I said before, it's space filled with air, but no gas exchange is occurring. There are two subtypes of dead space. The first is called anatomic dead space, and these are anatomic structures where gas exchange can't occur. And it's basically the conducting portions of the respiratory tract, so it's things like the nose and the trachea. The second type of dead space is called physiologic dead space. This is the anatomic dead space plus volume of alveoli that don't exchange gas. It turns out that not every single alveolus works just right to exchange gas, so some air goes to alveoli but doesn't get used. This is because of insufficient perfusion of blood usually. The apex is the largest contributor because it has less blood than the base. So physiologic dead space is all that space that doesn't participate in gas exchange. It includes the anatomic dead space, but also alveoli that don't work very well. And you should know that physiologic dead space is what increases in many diseases. When the lungs become sick, this isn't going to increase the size of your nose or trachea. The anatomic dead space is not going to change, but those alveoli that don't exchange gas are going to go up, and that means that the physiologic dead space is going to increase. There is a method for measuring dead space. It's not often done. It's an experimental method, and it will determine the physiologic dead space. It's called Bohr's method, and it's an equation that gives you the dead space from three numbers. So first you need the tidal volume. This is how much air goes in and out with each breath. So you have to hook the patient up to a machine and measure the volume of air going in and out with each breath. You also need to measure the amount of carbon dioxide in the air that the patient is exhaling with each breath. And then finally, you need to do an arterial blood gas and determine the CO2 concentration in the artery. Once you know those numbers, you plug it into this equation down here, which says the ratio of dead space, and remember this is physiologic dead space, not anatomic, it's physiologic. The ratio of physiologic dead space to tidal volume is equal to the arterial CO2 concentration minus the expired over the arterial. And this is sometimes done in different disease states to determine if the physiologic dead space has gone up or stayed normal. Okay, now let's review some basic principles about how we describe air pressure inside and outside of the lungs and about how air pressure creates air movement. So first of all, you should know that outside of our body, the pressure is equal to atmospheric pressure, which is 760 millimeters of mercury. However, by convention, we often describe this pressure as 0 millimeters of mercury, meaning that there is 0 millimeters of difference between the pressure and the atmospheric pressure. So anytime you see a pressure denoted as 0 millimeters of mercury, what they are trying to tell you is that the pressure is no different than atmospheric pressure. Now, if you think about your lungs at the end of inspiration, before you begin exhaling, there is no movement of air because you have completed inhaling a breath of air. At this point in time, the pressure in the alveoli is equal to atmospheric pressure. In other words, it's 760 or 0. And you know it must be equal to atmospheric because there's no air movement at the end of inspiration. Whenever there is no difference in pressure between outside the lungs and inside the alveoli, there will be no flow of air. When you begin to exhale, what happens is that the pressure inside the alveoli become positive, and we'll talk about why this occurs in a minute. But just so you understand the basic principles, let's assume that the pressure goes up to 765 millimeters of mercury, or +5. This will create a difference of +5 between the alveoli and outside the body, and that will drive airflow out of the body. When you take in a breath of air, the pressure in the alveoli becomes negative. In other words, it becomes somewhat lower than atmospheric pressure. Let's say it's 755 or -5. This creates a direction for airflow into the lungs, and therefore air will flow into our lungs. So these are just some basic principles of how we describe pressure and how pressure determines airflow. So now that you understand that, we can talk about the structures that create those positive and negative pressures inside our alveoli, and that is the lung and chest walls. Now, in order to understand how our lung and chest walls work together to modify the pressures in our alveoli and create movement of air, you have to understand two basic principles. The first one is that the lung's general tendency is to collapse. Your lungs, if left to their own devices, want to collapse and pull inward and recoil. You can think of your lungs like a balloon, and if a balloon has no
no forces pushing out on the walls, it will collapse into a crumpled ball on the floor. That's how you can think of your lungs. Your chest wall, on the other hand, likes to expand. If left to its own devices, the chest wall has all those muscles and they like to push out to the sides and expand, and therefore your lungs prefer to sit relatively stretched far apart with some volume of air in between them. In other words, your lungs like to spring outward. And these two principles here are very important in order to understand how the lung and chest walls work together to create air movement. So let's drill down on this a little further, and let's begin by talking about the lung first. So the relationship between volume and pressure in the lungs looks like what I've drawn on the screen here. So if you put no pressure into our lungs, in other words, if there's no air pressure filling the alveoli, the lungs will tend to have no volume. Like I described in the last slide, they will collapse like that crumpled balloon on the floor. If you begin to apply pressure to the walls of the lung, they will start to increase in size. In other words, they will begin to expand in terms of their volume up to a maximum point beyond which it gets very hard to expand them even further. In other words, even if you add lots and lots of pressure, you don't get much volume once you get out to a certain point. And this is the pressure-volume relationship of the lungs. The chest wall, on the other hand, has a pressure-volume relationship that looks like what I've shown on the screen here. If you apply no pressure to the walls of the chest, it will still have a volume.